Last week, we talked about the power transmission system, the gear system, and we have introduced these 5 important rules. I hope you have tried hard to understand and remember these 5 basic rules in power transmission system. Okay, so especially the rule number 4, if you still remember, rule number 4 said that when the 2 gears are connected with a shaft, well, their angular velocity will be the same, right? Their torques will be the same, right? But torques are the same. This is rule number 5, right? Rule number 4 said their angular velocity will be the same, but their angle of twist will not be the same, will not be equal to each other. Why some students didn't understand this, and they asked me, and I have told them that this would be our task next week, right? That is what we were talking about here. It is the angle of twist in gear assemblies. Okay, so this will be a new section, and we will have more time left, and then we will solve some indeterminate problems in torsional elements. Okay, I have mentioned in the beginning of this chapter and at the end of last chapter that you have to understand the basic principles to solve indeterminate problems, since later we will have indeterminate torsional elements, indeterminate beams, okay? But the principles to solve these indeterminate problems will be the same, right? This means you cannot find enough equations to solve internal forces based on equilibrium equation. You have to find additional extra equations from compatibility condition, okay? To make sure that you have the same number of equations as the number of unknowns, and you can solve them simultaneously. Right, so that is the principles, and our objectives today: calculate the angle of twist in gear assemblies and solve indeterminate problems in torsional elements. Okay, so previously we have talked about the gear assemblies and important concept called gear ratio, and we also introduced the 5 rules. Right? So the gear ratio, what is gear ratio? Gear ratio is just when you can only define gear ratio when 2 gears are directly connected to each other, right? As shown here in this figure below, we have 3 gears, they're connected to each other. If we call this smallest one is gear A and this is gear B, and consider that we have a power transmission from A to B, right? So the gear ratio AB can be calculated from dB over dA, or RB over RA, a diameter or radius, doesn't matter, or number of teeth of B over number of teeth of A, right? So this is the gear ratio. Okay, so when 2 gears are connected through a shaft, well, you cannot define gear ratio, even though their sizes are not the same, but the gear ratio is just invalid, okay? And then the 5 rules, let's basically review these 5 rules. And the rule number 1 said what the P, the power, equals torque times omega, torque times angular velocity. That is a constant, right, through the whole system, through the whole gear assembly. Okay, so anywhere you have smaller torque, the angular velocity will be larger. Right? Anywhere you have a smaller torque, larger torque, the angular velocity will be lower, will be smaller. Okay, so their product will be a constant. That is the constant power rule. This is rule number 1. Then rule number 2 and the rule number 3, those are just for 2 gears. For 2 gears directly connected. So for example here, right, in this example, we have a gear ratio AB, right? So if this gear ratio AB is larger than 1 or smaller than 1, okay, in this case it's larger than 1, right? So if your transmission is from B to A, then the gear ratio BA will be smaller than 1. Okay, so strictly speaking, this gear ratio, this value depends on the direction of the transmission. Okay, so in these two gears directly connected and power transmission from A to B, right, this is our assumption, is from A to B. And here the rule number 2 says that if you have a larger gear, the torque will be larger, right? Torque will be larger. So meaning that the TB is larger than T1, TA, right? Or TB equals negative gear ratio AB times TA, right? This is our rule number 2. And rule number 3, when you are transmitting from a smaller one to a larger one, then the angular velocity and angle of a twist will be smaller, right? So phi B is smaller than phi A, or phi B equals phi A over gear ratio negative, okay, gear ratio AB. And this phi here can be replaced by omega, right? So they follow the same rules. So here, if the omega B, omega A, omega B, and the omega A here, just they also hold this rule. Okay. Then if two gears are connected through a shaft, then we will have our number 4, such that the omega B equals omega A. 5 would be TB equals TA, right? But here we didn't say that phi B equals phi A, right? So this is incorrect. How could this be incorrect? We will analyze this here, okay, in this section. Okay, this is a new section called angle of twist in gear assemblies. Okay, as we just briefly introduced, just look at here. If we have this A and B, these two gears, A is here, B is here. Okay, these two are just connected through a shaft. Then this is moving along a shaft. This will follow our rule number 4. This just describes our rule number 4. Right, this omega A equals omega B, but phi B doesn't equal to phi A. They have a difference. The difference is just right here, the phi 1, right? Because they are connected through this shaft 1, okay, this shaft 1 will be twisted, okay? So you can imagine that if you assume that the A will not change, the A will not be rotated, but phi 1 will be rotated because of the internal torque, then the B must have a angle of twist larger than A, and the difference is just a phi 1, right? So we got this equation. Okay, phi B equals phi A plus phi 1, right? Because the shaft will be twisted. And the angle of a twist in shaft 1, this phi 1, it just can be determined from T1 L1 over G1 J1. Okay, the T1 is the internal torque that you need to determine from free body diagram. Okay, then if moving between gears, right, as shown here, moving between gears A, B. Okay, so here this a phi B will be, phi B and phi A will be connected by negative gear ratio. Okay, so some students told me that this is very confusing. Right? Sometimes, well, you will have multiply gear ratio, sometimes over gear ratio, and sometimes gear ratio is larger than one, sometimes gear ratio is smaller than one. Right? This is very complicated. But here I'm introducing a golden rule. Okay, I'm introducing this golden rule. So to solve these confusions, okay, this is summarized. I summarized in last semester. So perhaps you cannot see it in any textbook, but it's very useful. Okay, this is very useful. So I call it golden rule. Okay, I used this color. Call it the golden rule. Okay, those. Let's just simplify these 5 rules. This rule number 2 and rule number 3. Okay, let's simplify rule number 2 and rule number 3 into this golden rule. Okay, this is sometimes you have gear ratio like a gear ratio AB larger than 1, gear ratio BA smaller than 1. Sometimes multiply, sometimes over. I just let's simplify this. Okay, keep in mind that the nature of rule number 2 and rule number 3 is when 2 gears are connected directly, the larger one always has larger torque but a smaller angular velocity and smaller angle of a twist. Okay, and the smaller one always has smaller torque and a larger angular velocity or larger angle of twist. Okay, larger gear. Okay, only in this case when these 2 gears are directly connected. Okay, only when they are directly connected. Rules number 2 and number 3. We're talking about 2 and 3. Okay, when they are directly connected and you can define a gear ratio, the larger one, the larger gear, always have larger torque and smaller angular velocity. Okay, so this is the golden rule. And always use this criterion to examine your results or calculation. After your calculation, you just use this golden rule to examine, to check if your results are reasonable, make sense. Just look at the larger one, compare it with the smaller one. If your larger one got a larger torque and smaller angular velocity and smaller angle of twist, if yes, your result just makes sense. Otherwise, you made some mistake. Okay, you have to recalculate it. Okay, this is our golden rule. So in the later examples, I will show you how to apply this golden rule. Okay, how to use it in practice. Okay, here before the first example, let's just examine these 2 simple cases. Okay, in case 1, you don't have any gear. Okay, it's just 2 shafts are directly connected. You can see that if you want to determine the angle of a twist at the end D, okay, our target is to determine the angle of a twist at D, at this point D. Okay, okay, in this case 1, you just have these 2 sections, shafts 1 and 2 connected together, and they are fixed at point A. Okay, then you add a TD at the end D, and you are requested to calculate the angle of twist at D. Okay, this is the old problem. Okay, this is the old problem. You can just determine the internal torque T1 and T2. In this case, if you have been familiar with the free body diagram and how to determine the internal torque, you can directly give the answer, right? The T2 equals TD, T1 equals T2 equals TD, right? So if you determine this internal torque, and you have node L, G, and J, right? So you can calculate phi 1 and phi 2, then add them together, you'll get phi D, right? There's no gear ratios, no gears in this system. But how about case 2? Case 2 will be more complicated. So the shafts are connected by gears, okay? Here you have a shaft 1 fixed at point A, then it's connected to B, okay? connected to gear B here. And B is connected to gear C. Here you can define a gear ratio. Okay, here you have a gear ratio. Then from C to D, it's connected by a shaft 2. Okay, then one torque is added to point D, and you're requested to determine the angle of the twist at point D. Okay. Of course, here, so you can determine the internal torques, T1 and T2, then determine phi 1 and phi 2. But here, because of the gears, you cannot calculate phi D from phi 1 plus phi 2. This is wrong, okay? Because of the gears connection, okay? So you have to do this analysis from the fixed end to figure out how to determine this phi D, okay? From the fixed end, phi A equals what? Phi A equals 0, right? Because it's a fixed end. Then here you have a phi 1. You have a phi 1. Then the B, at the point B, this phi B equals phi 1 equals phi 1 plus phi A, right? Because phi A is 0, just equals phi 1, right? So this is just our rule number 5, rule number 4. Okay, this is our rule number 4. Okay, then from B to C, you will get a phi C equals our original equation said that phi C equals negative phi B over phi BC. Right? Since that is very confusing, as I mentioned several times, so you can just ignore those things. You just use the golden rule. Just use negative gear ratio times phi B. And then you can determine if this gear ratio is larger than 1 or smaller than 1. Okay. According to the golden rule, is from B to C. Since C is what C is a smaller gear. A smaller gear always have smaller torque, but larger phi, larger omega. Right? Okay, so here in this equation, this gear ratio should be larger than 1. Okay, larger than 1. When it's larger than 1, you just use the diameter of the larger gear over the diameter of the smaller gear. Okay. Then after the phi C, then phi D will be phi C plus phi 2. Okay. So to summarize these equations, you will get that phi D equals phi 2 plus phi C, right? Phi D equals phi 2 plus phi C, and phi C equals negative gear ratio times phi B or phi 2 or phi 1. Okay, you get this equation. Okay, you can see that it's not equal to phi 1 plus phi 2. It equals phi 2 minus gear ratio times phi 1 because of these gears. Because these gears, this will introduce a negative sign into here. Because when you add this TD, your C, gear C will be turning in this direction, but B will be turning in opposite direction. So you will have a negative sign in this equation. Okay, let's give some numbers to solve this problem in example 1. Okay, the shaft 1 is fixed at support A. It's just exactly the same as these two cases. Just give you some numbers, and the TD equals 300 Newton meter at the right end. Then other conditions that we have introduced, just diameters 1 is 35, diameter 2 is 25, and the teeth numbers have been given. NB is 60, and C is 20. And length L1, L2 have been given, and the shear modulus have been given. Okay, so let's see how to solve this phi D in two cases. Okay, in case one, no gears. Okay, as we mentioned, this is a old problem. Old problem, so we just solve it simply. So this is our case 1. This is our case. This is our case 1. So we will start from what? From free body diagram to determine internal torques, right? Free body diagram. From this first free body diagram, okay, you just cut it here and make it free. Then you will get that T2 equals TD, equals 300 Newton meter, right? It is 300 Newton meter. So this will be 300,000 Newton millimeter. Then how about T1? Shown here in the second free body diagram. T1 is also TD, right? 300,000 Newton millimeter. Okay, then we can calculate these things. You just need to know this L1, L2, G1, G2, J1, J2, right, etc. Right, so here just we determine these parameters. Like L1 is 500 millimeter, L2 is 350 millimeter, and G1 equals G2, since they are the same material. This is 77 GPa, right? But we need MPa, so this will be 77,000 MPa. And the J1 can be calculated from pi over 32 times D1 to the 4th. So it will be pi over 32 times D1 is 35 to the 4th. This will be 147,300 millimeter to the 4th. And J2 will be pi over 32 D2 to the 4th, pi over 32, and the D2 is 25. Okay, so this will be 38,350. Then this angles of a twist can be calculated, right? It's a phi 1 equals T1 L1 over G1 J1. So get all of these numbers in. I have turned all of them into Newton millimeter MPa, right? So you can just use these numbers, right, to calculate the results. This will be 0.01323 radian. And the phi 2 will be T2 L2 over G2 J2. So it will be 0.03556 radian. So our phi D will be phi 1 plus phi 2. Right, this will be 0.04879 radian. Okay, I want to emphasize it again. So later in next week, two weeks later, you will have a second midterm exam. Okay, pressure is coming again. So we just make sure that you can do the correct calculations. Okay, so here I skipped something. It's shown here. I skipped these calculations, but you should try these calculations by yourself. Okay, use your calculators to try to check this result to see if you can get the same results or not. Okay, so in calculations, you will always encounter some troubles like selecting numbers, do the calculation, and get the correct answer. Okay, try to do more exercises in using your calculator to get the correct results. Okay, this is the old case 1, and in case 2, this is what we talked about today. Okay, this is our case 2. As we mentioned, to start from the free body diagram to determine T2, right? So we can determine T2 from free body diagram, just here, right? This is T2 equals TD, that is 300,000 Newton millimeter. I then, following this shaft from D to C, okay, this is our rule number 5. Right, this is our rule number 5. Right, from rule number 5, we can get that TC equals T2. Right, that is 300,000 Newton millimeter. Right, then how about TB? How about TB? TC to TB is the 2 gears directly connected. So we can define a gear ratio. All right, so this is our rule number 3. Rule number 3. TB will be, right, just from C to B, right? TB equals, we just use the golden rule, we ignore the direction, so we just use a negative gear ratio times TC. Right. We just need to figure out if this gear ratio is larger than 1 or smaller than 1. Okay, which one has a larger T? TB or TC? Which one is larger? Which one is larger? Jackson Riggs.
Can you hear me?
Yes.
Hello?
Hey.
TB is larger. I got muted again. Sorry.
Okay. So here this TB is larger. So what is the gear ratio here in this case? Just in this equation we're showing here, TB equals negative TR times negative gear ratio times TC. Okay, you said TB is larger. So if this gear ratio is larger than 1 or smaller than 1?
Larger.
It's larger than 1. So how to calculate this gear ratio? We have known that the NB is 60, NC is 20. Okay, so what is the gear ratio?
3.
Okay, great. Great. That is the correct answer, right? So here, so we got a negative 60 over 20 times TC. Okay, so this is just our golden rule. Okay, our golden rule said you can ignore the real numbers of the gear ratio. Or just do this analysis. A larger gear will always have a larger torque. Right, just multiply the smaller torque and a gear ratio larger than 1. Okay, so this is the golden rule. Saying here is equals negative 3 times TC. This will be negative 900,000 Newton millimeter. Okay, we got TB. Then from TB to T1, TB, the B and 1, shaft 1 connected together to point A, right? So our TB, T1 equals TB. Okay, that is negative 900,000 Newton millimeter. This is our rule number 5 again. Okay. So after that, we can calculate the angle of twist in each shaft. Right? We can calculate the phis in each shaft. We have 2 shafts, 1 and 2. Right? So phi 1 is just T1 L1 over G1 J1. And the numbers have all been there, right? Keep them all in Newton millimeter MPa. So you can get the result is negative 0.0397 radian. And phi 2 will be T2 L2 over G2 J2. So it will be positive 0.0355 6 radian. Again, I ignored here. Okay, I skipped this calculations to try it by yourself. Okay. Then the phi d. Okay, we're determining phi d. Okay, how to determine this? We have derived that equation, okay, in previous slide. Let's do it again. Okay, phi d equals what? Phi d equals phi d equals phi 2 plus phi c, right? Equals phi c plus phi 2. Okay, just here. Through this shaft 2, phi d equals phi c plus phi 2. And what is phi c? Phi c is negative gear ratio times phi b plus phi 2. Okay, so here we are getting another gear ratio. But here, if this gear ratio be 3 or 1/3. Okay, again, here we're also using the golden rule. Okay, when it's from phi c from phi b to phi c. Okay, look at B and C. Okay, B is larger, C is smaller. Okay, so here we're actually calculating phi C from phi B, and we're using negative gear ratio times phi B. Right, which one is larger? Phi C and phi B, which one is larger? Let me find another student here. Macklin Jenselmeyer.
Can you repeat that one more time? Sorry.
Yeah. Oh, it's okay. Here, so I'm asking, look at this equation. We're calculating phi C from phi B. Okay. The angle of twist of gear C, here is C, from the angle of twist of gear B. Okay, we're connecting them using a gear ratio. Okay, I'm asking phi C and phi B, these two values, which one is larger? C is a larger gear, B is a smaller gear. For phi C and phi B, which one is larger?
Phi C is larger.
Phi C is larger because it's a smaller gear, right? Mm-hmm. So if in this equation, if we're connecting these two phi values using a gear ratio, should this gear ratio be 3 or 1/3?
3. Okay,
great. That is okay. So I hope you have seen that the golden rule works very well. Okay. So here, this again, we're just using a 3, okay? And this phi B just equals what? Equals phi 1, right? So here we get negative 3 times phi 1 plus phi 2. Okay, so here we have these numbers already. So negative 3 times phi 1 is negative 0.0397. By plus 0.3556. Okay, so here the result will be positive 0.1546 radian. Okay, so this is the example 1. You can see that it looks very, very complicated, multiple steps. But if you understand the golden rule, always keep in mind that when you have just when the two gears are connected directly, the larger gear always have larger torque, smaller phi, smaller omega, and smaller one will always have smaller torque, larger phi, and larger omega. Okay, always keep this in mind, and then play with the gear ratios, calculate the gear ratios. Since there are only two possibilities for this gear ratio, one is larger than one, another is smaller than one. Okay, just select the correct one to do your transmissions of T, of phi or omega. Okay. Then this is example 2. Potentially more steps because more sections, but if you understand, again, if you understand the golden rule, everything will be just natural, just sequential, okay, from one end to the other end, it's step by step. Okay, this a long shaft, two shafts. Okay, shafts are made of steel. As G has been given, each has a diameter of D. The D is a constant. Okay, but two shafts have the same diameter, and gears B and C are connected together, and a torque of TD is applied on gear D, and the torque TE is directly applied to shaft at E. Okay, we add two external torques and determine the angle of twist at D. Okay, at D, not at the end E. Okay, we're determining D. So gear diameters have been given, so you can calculate the gear ratios. Then the length L1, L2, these two torques have been given. Okay, this is just a sequential thing. Okay, this let's analyze this. How to determine this phi D? Okay, how to determine phi D? Okay, since we have a fixed end at point A. Okay, so this point A will have a phi A equals 0. Okay, phi A equals 0. So we can just start from this fixed end, step by step, then we can get this phi D. Okay, so from A to 1 to B, we can know that phi B equals phi A plus phi 1. Right? Since phi A equals 0, this equals phi 1. Okay. Then from B to C, phi C equals, again, our golden rule, negative gear ratio times phi B. Okay, this is our rule number 3. Okay, this is our rule number 3. So the question is, if this gear ratio is larger than 1 or smaller than 1, okay, phi C, calculating phi C from phi B, okay, C is a larger gear, C is a larger gear, so phi C will be smaller than phi B, right? So this gear ratio is smaller than 1, okay? This is a smaller than 1 gear ratio. Then from C to D, okay, we're calculating phi D, right? So phi D equals phi C plus phi 2. Okay, so we have derived how to calculate phi D, right? So from phi B, from phi 1 to phi B to phi C, then to phi D, okay, several steps. Here, can you see that how can we finish these calculations? You need to know phi 1 and phi 2, right? So you have to know phi 1 and phi 2. But how to calculate phi 1 and phi 2? You have to know T1 and T2. Okay? So we will have several steps. Step 1 will be determining T1 and T2. Then step 2, determining phi 1 and phi 2. Then step 3, just using these several steps to solve this phi d. Okay. Then let's look at the first step. First step, to calculate T1 and T2, we have to start from a free body diagram. Okay, free body diagram. Here I have given several free body diagrams, like a free body diagram 1, and this is the free body diagram 2, then 3, and 4. This is the fourth free body diagram. Okay. Since 1 has a fixed end A, you'd better not using it. Right, just B and C are connected to that one. So the free end will be the free body diagram 4. Okay, free body diagram 4 here is the real free end. Okay, we're just starting from here to calculate T2. Okay, based on this, we have TD and TE. Okay, use your right hand rule. Okay, TD, curl your 4 fingers with the direction of D, then your thumb will be pointing right. Okay, so your TD will be pointing right, and TE will be pointing left, and T2 pointing outward, that will be left. Okay, so you will get negative T2 plus TD minus TE equals 0. Okay, from here, you will get T2 equals TD minus TE. TD is 10, TE is 2. 10 minus 2 will be 8 kilonewton meter. Okay, then you can use free body diagram number 3. Right? Free body diagram number 3 here, so you can directly get that TC equals T2, right? Or use our rule number 5, right? Since they're just connected, this shaft is connected to this gear, so they will always have the same torque. Okay, this is TC equals T2 equals 8 kilonewton meter. This is either from rule number 5 or free body diagram 3. Okay. Then from TC to TB, from TC to TB, okay, you have a gear ratio here, right? This, you will use rule number 2. Right? Rule number 2, we're calculating TB from TC. Okay, again, we'll just use our golden rule, negative gear ratio times TC. Okay, TB and TC, which one is bigger? Which one is larger? Torque B, torque C, which one is larger? B is a smaller gear, right? So it will always have smaller torque. So this gear ratio will be smaller than 1. Okay, this gear ratio will be smaller than 1. If it's smaller than 1, we just get negative CD, C and B. So the dB is 150, the other one is 200. Okay, so negative 150 over 200 times TC, that is 8. Okay, it's 3/4 times 8, you get a negative 6 kilonewton meter. Okay, then T1 equals TB, right? Equals negative 6 kilonewton meter. This is again either from rule number 5 or free body diagram 1. Okay, let me note it here. So rule number 5 or free body diagram 1. Okay, this is our 1, 2, 3, and 4. Okay. Okay, so we have determined T1 and T2. Okay, this is our target. Okay, determine T1 and T2 in the first step. We're done, so we can move to the step 2 to calculate the angles of the twist in these two shafts. Okay, so our step 2, determine phi. Calculate phi's. Okay. So before that, we need to determine the J values. Right, so J1 equals J2. Right, this will be just a pi over 32. Diameter 80 to the fourth. So it will be 4.02 millimeter to the fourth. Then we can calculate phi 1 and phi 2. Right? Phi 1 equals T1L1 over G1 J1. It will be -6. -6. T1 is -6 kilonewton meter. Okay, I will use -6 times 10 to the 6 to turn it to Newton millimeter. Okay, be clear why we added this thing. Okay, this thing here is converting Newton is kilonewton meter to Newton millimeter. Okay, so we're adding this 10 to the 6, the million here. Okay, so L1 is 600 millimeter. Okay, over G 75 GPa. Okay, we want MPa. Okay, again here this thing is converting GPa into MPa. Okay, times J1. So it is just a 4.02 times 10 to the 6 millimeter to the fourth. Okay, so here we will get the phi 1 will be negative 0.0119 radian. Okay, then phi 2 will be T2 L2 over G2 J2. Will be 8 times 10 to the 6 times the length will be 600, the same. Okay, and here will also be the same, 75 times 1000 times 4.02 times 0 times 1 million. So this will be positive 0.00159 radian. Okay, the third step, since we have analyzed, we will have, this will be our third step. Okay, from here to here. This is our third step. Okay, so phi b equals phi 1. Phi b equals phi 1 equals 0.0159 radian. Then phi c equals a smaller than 1, as analyzed in the beginning here, is a smaller than 1 gear ratio times phi b. That is a negative 150 over 200 times 0.0159. So will be this is phi 1. Okay, So here will be 0.0 negative 0.0119 radian. And here will be negative 0.0119. Then the result will be positive 0.0089 radian. And the last step will be phi d equals phi c plus phi 2 will be 0.0089 plus 0.0159 will be 0.0248 radian. Okay, so here we are done with these calculations. We have determined the angle of twist at gear D, okay? But so we asked you determine this angle of twist at the point D. Then how about E? If I request you to determine phi E, how will you do that? Okay, how will you do that? You can just do what? Do free body diagram. From this, you can determine that the T3 equals negative TE, right? Negative TE, right? Because TE is a negative value, okay? And this will be negative 2 kilonewton meter, right? Then the phi 3 can be calculated. So it will be just a T3 L3 over G3 J3. Then the phi E equals what? Equals phi D plus phi 3, right? Phi D has been determined here in this third step. Then how to get phi 3 and phi E, okay? In-class assessment, okay? All right, I have to push you to do more exercises, okay? This is our in-class assessment. Again, I just embed it. I'm embedding it in this video, okay? Because since we have only 20 students here, we'll have 40 students. I hope them watch the video carefully to dig out this in-class assessment and submit it, okay? This is our in-class assessment today. Okay. In the end of example 2, okay, of this section. Then in the rest of time, let's look at indeterminate problems, okay? Indeterminate problems. I forced you guys to do more exercises of the indeterminate axially loaded element, right? I suppose that you have been much more familiar than the situations before the first exam with these indeterminate problems. Okay, here you will see that if you have understood those indeterminate axially loaded elements, here the indeterminate torsional element will be super easy since the principles are exactly the same. Okay, so what is indeterminate torsional elements? Again, this just means from free body diagram, okay, from equilibrium equations, you cannot solve the internal torques. Okay, in the previous examples, you have seen that we always need to determine the internal torques first. Use the internal torque to determine the phi values of each shaft, then use them to solve some problems. Right? So if you cannot determine the internal torques from free body diagram, what you can do? What can you do? Okay, you have to use these principles to solve the internal torques, then use them to calculate phi values to solve other problems. Okay, so here again, so what is indeterminate torsional elements? It's just you cannot build enough equilibrium equations to solve all the internal torques. Okay, then what can we do? Again, based on the principles from the last chapter, you have to establish extra equation based on compatibility, okay? You need to check the compatibility or the geometric correlations between different elements, then to build a additional additional equation to solve the problem. Okay, so how to solve it? We will have 4 steps, exactly the same as the indeterminate axially loaded elements. Exactly the same 4 steps. The first step will be free body diagram to get the equilibrium equation. The second step, establish the twist torque, or just the load deformation equations. Previously, we just need to list the delta equals FL over EA, right? So here you just need to use phi equals TL over GJ. Okay, this will be very similar. You can do analogy to the previous chapter. Okay, the first step, equilibrium equation. The second step, just phi equals TL over GJ. The third step would be equilibrium, the compatibility condition. Then the fourth step will be just get these 2 equations together to solve 2 unknowns simultaneously. Okay, so here just see here in what conditions we cannot find these equations, enough equations to solve internal torques. Okay, the first one will be the same, very similar to the first case in the last chapter. Okay, you have 2 sections connected together. On both ends, they are fixed. Okay, meaning that at point A and point C, okay, point A and point C, no phi will be allowed. Okay, even though you will have phi 1, you will have phi 1 here, you will have phi 2 here, but phi A will be 0, phi C will be 0. Okay, meaning what? Meaning phi 1 plus phi 2 equals 0. Okay, phi 1 plus phi 2 equals 0. And here in the second case, okay, you have 2 elements bonded together or connected using, just be familiar with these keywords. Okay, they are perfectly bonded together, or they are just connected using using 2 rigid plates. Okay, in the descriptions of problem, you can see this kind of words. They're either bonded together perfectly, or they are connected using rigid plates at the end. Okay, then we can assume that they will always rotate together. Meaning what? Meaning they will always have the same angle of twist. Okay, so phi 1 equals phi 2. These are the 2 situations based on which you can get different compatibility equations. Okay, so we will show this. We will analyze this in 2 examples. Okay, this will be simpler. This will be even simpler than the axially loaded elements. Okay, since we very likely will not induce any gaps in the systems, and it will not have proportional things like a similar triangle stuff. You have only these 2 situations. Okay, situation 1, phi 1 plus phi 2 equals 0. Situation 2, phi 1 equals phi 2. These are the 2 possibilities, only 2 possibilities. Okay, this will be easier than the last chapter. Okay, let's look at the first example. Okay, the torsional assembly in this figure consists of solid 50 millimeter diameter segment 2 is securely connected at flange B to a solid 80 millimeter diameter steel segment 1 to determine the maximum shear stress magnitude in shaft 1 and 2 and the rotation angle of flange B relative to support A. Okay, we're determining tau 1 and tau 2 maximum values. Okay, how to do this? Of course, tau equals TC over J. Okay, T will be a constant, J will be a constant to just find the largest, the C value. This is the rho max, right, equals the radius, half of the diameter, right? So you have to determine T1 and T2. Okay, you just need to determine T1 and T2. Then the B will be rotation angle of B respect to A. Okay, although phi A, phi C both equal 0, but phi B can be a non-zero stuff. Okay, the flange B can be rotated. So we're actually determining phi 1, right? Since phi B equals phi A plus phi 1, phi A equals 0, right? So just phi B equals phi 1. And what is phi 1? Phi 1 just a T1 L1 over G1 J1. Again, you just need to determine T1, okay? So you can see that for both of these questions, these problems, you have to determine the internal torques T1 and T2. So how to do that? We have to start from a free body diagram. Right, start from a free body diagram to try to find the internal torques. So the first step, free body diagram. Cut it from here, right? So you will get a bigger section, smaller section. The TB, a right-hand rule, TB will be pointing right. TB here, T2 here, T1 here, okay? So negative T1 plus TB plus T2 equals 0, okay? Or T1 minus TB minus T2 equals TB. And TB is 12 kilonewton meter. Okay, this is our equation 1. One equation, 2 unknowns, you have no way to solve them. Right? You have T2, T1 and T2. So we have to follow our 4 steps to solve this indeterminate problem. Right? So the second step will establish the twist torque correlations. Okay, these correlations. Okay. Phi 1 equals T1 L1 over G1 J1. All right, so here we have known a lot of these parameters. L1 is 450 millimeter. Right, G1 is 86 GPa or 86,000 MPa. Then the J1 will be pi over 32 times D1 to the fourth, that is 80 to the fourth. You get a 4.02 million millimeter to the fourth. Okay. So get these numbers in here. So you will get T1, since T1 is unknown, okay, you cannot get a result, you will get an expression. Okay, T1 over 768 million. So in the same way, you will derive that phi 2 equals T2 L2 over G2 J2 equals what? We have known a lot of values, where L2 equals 200 millimeter. G2 is 45,000 MPa. J2 pi over 32 times 50 to the fourth. You will get 0.614 million millimeter to the fourth. And again, this from these numbers, you can calculate it. Then this will be simplified into T2 over 138 million. Okay, so the third step would be compatibility. Okay, as we just introduced in the previous slide, in this case, since both ends have been fixed, so no overall deformation, no overall angle of twist will be allowed. So just a phi 1 plus phi 2 equals 0. Okay, from what we have got, you will get T1 over 768 million plus T2 over 138 million equals 0. Right, from here, you can get T1 equals negative 5.57 T2. This is our equation 2. Okay. Then you can get equation 2 into equation 1 here. Right. So we'll get you can solve that. T2 equals negative 1.82 kilonewton meter, and T1 equals 10.18 kilonewton meter. Okay, so we have solved this T1 and T2, then the question A and question B can be answered. Question A is just to calculate tau 1 max. That would be just a T1 C1 over J1, right? But here, this T1 is 10.18 kilonewton meter. Okay, we need Newton millimeter, right? Times 10 to the 6 Newton millimeter. Okay, again, here we are using this parameter to convert kilonewton meter into Newton millimeter. Okay, so this one times the C is just 80 over 2 over J is 4.02 million millimeter to the fourth. And here you will get 101.2 MPa. Then in the same way, tau 2, the maximum values of tau 2 would be T2 C2 over J2. Here will be 1 point, since they're asking magnitude, okay? So the negative sign is just not needed. Okay, 1.882 times a million times 50 over 2 over 0.614 million, 74.3 MPa. Then step B, we're calculating what phi B, right? Phi B equals phi 1, right? This will be T1 L1 over G1 J1. Okay, this has been simplified into here, right? T1 over 3, T1 over 768 million. Okay, just T1 over 768 million. The T1, you should use 1 Newton millimeter, right? Since in the previous calculation you have been using Newton millimeter MPa, right? So here would be 10.18 million over 768 million. So it would be 0.0132 radian. Okay, so this is our example 1. Then example 2 will be exercise of another scenario, just when these two are perfectly bonded together. Well, in this case, you can see that these two segments are connected by rigid plate, meaning that they will always be rotated in the same way. They will always have the same phi values, okay? A composite shown here is to have two components. You have a steel, that is 2 is a steel, and 1 will be a tube, aluminum tube, okay? And you add a torque T equals 1,100 Newton meter. Then determine the maximum shear stress and the rotation angle of B relative to A. Okay, this is asked basically the same thing as example 1. Okay, you just kind of start from the equilibrium equations. We have the 4 steps, right? From the free body diagram that is shown here, right? So you're adding these two internal torques. You have two internal torques, right? It's a T1 and a T2. Okay, T1, the T2, this is T2 and T1, both pointing left, and your T2, your T, external T is pointing right. Right, so you will get T1 plus T2 equals T. Right, so this is our equation 1. Then the second step, you will get the phi 1 equals what? T1 L1 over G1 J1. Phi 2 equals T2 L2 over G2 J2. And here, since L1 equals L2, right? So it can be simplified a little bit. So our third step, compatibility. In this case, compatibility equation is phi 1 equals phi 2. Right? From here, you will just get T1 over G1 J1 equals T2 over G2 J2. Okay, since L equals to each other. It can be deleted. Okay, then from here, this you will get our equation 2. Right? In the fourth step, you get equation 2 into equation 1. Then you can solve T2, then T1. Okay, then use T1 and T2. You can solve the internal torques, the shear stresses, and tau equals TC over G, or over J, TC over J. Right, then B will be, you're calculating phi AB, right? So this equals phi 2 and equals phi 1, right? Since they are the same, right? Because of the rigid plates, they will always be equal to each other. Phi 1 and phi 2 will be always equal to each other, okay? So just get numbers in so you can get the results, okay? I will give you the steps and the results. I will just get all of these results in the slide, in the handout. You can do your own exercise. Just to try to follow these tips, okay? Follow these tips that have been given. Try to do this exercise by yourself to check if you can get the correct results.